Okay, so we're going to look today at section 2.6. A lot of what we're doing today is going to be involving graphs and graphing piecewise defined functions. So what they're going to have us do first of all is just we're going to get a bunch of base functions. So we have what's called the identity. We have what's called the squaring function. We have the cubing function. So identity function is y equals x. Its graph is a diagonal line like this with slope 1 that passes through the origin. The squaring function is the base parabola. Its equation's y equals x squared. Its graph looks like this. And for when we use this for section 2.7 to move this graph around, couple points of interest. We have the points 1, 1 and negative 1, 1 are on the parabola, so it's a good idea to kind of note that those points are there. I guess on this one we should note it passes through the point 1, 1 and the point negative 1, negative 1. So these are kind of, as you're moving stuff around, these are some important points you can use to make sure you're getting the shape of the graph right. Cubing graph is y equals x cubed. So its graph looks kind of like this, hits the origin and comes on down. And some other points of interest on it are 1, 1 and negative 1, negative 1. So we have kind of these initial graphs here. We're going to end up with a total of, I think, about 9 of these before we're all done. So we're going to say for these, domain, since this is a diagonal line, the domain and range are both all real numbers. For the squaring function, the domain, this graph exists for all x, so the domain is all real numbers. The range, however, you only start at 0 and get positive numbers, so the range is 0 to infinity. And for the cubing function, this is kind of similar to the diagonal line. It hits all x values. The graph exists for every x. And for every y, the graph passes through it. So its domain and range are both all real numbers as well. So this is the initial group of 3. Next group of 3, we got absolute value, we got square root function, and we have the cube root function. So next we get absolute value, whose equation is y equals absolute value of x. We have the square root function, whose equation is y equals square root of x. And we have the cube root function, whose equation is y equals cube root of x. So for absolute value, we have basically a V shape like this. For square root function, we start here at the origin and we trail off to the right. And for cube root function, we trail off to the right and we trail off to the left as well. Domain of this is all real numbers. The range of this one, it exists for 0 and positive y's. For the square root function, the domain starts at 0 and goes off to the right. The range also starts at 0 and goes up and hits y values above. And for the cube root function, the domain, it exists for all x's, so its domain's all real numbers. Its range, it eventually gets to all the y's, so its range is all real numbers as well. So this was kind of the first group of 3 here. This is the second group of 3. And then the final ones that we have are the reciprocal function, the square of the reciprocal function, and one called the greatest integer function. So the reciprocal function, this is y equals 1 over x. Its graph has a vertical asymptote at 0 and a horizontal asymptote at 0. So it comes down and it approaches the x and the y-axis, but doesn't actually get there. And this one does kind of a similar thing. Its domain is everybody except for 0, and its range also, since neither of them hit the x-axis, also skips 0. So for the reciprocal function, domain and range, it takes all other values except for 0. We have the square of the reciprocal function. This is y equals 1 over x squared. So its base graph looks like this. And its domain is the same as the domain. It has a vertical asymptote at 0, so it's the same as the domain of the reciprocal function. Its range, however, now you can't get back negatives. These are both are above the x-axis. They never hit the x-axis. So its range is 0 to infinity. And the final one we have here is called the greatest integer function. And its graph looks like a step function here. Start at 0 with the closed dot. We go to 1 with an open dot. We jump up. We got 0 with a closed dot, 1 with an open dot. We jump up, 0 with closed dot to 1 with an open dot, etc. And same down here. 0 with closed dot to 1 with an open dot, and 0 with the closed dot to 1 with an open dot. So the domain on this, everywhere there's an open dot, there's a closed dot that's above it, so it never skips an x value, so its domain's all real numbers. Its range, however, you only y values where this exists is positive and negative whole numbers, so we get 0, 1, 2 on up, and we get -1, -2 on down. So basically, the greatest integer function, it's the function that you can kind of think is always rounding down. Its symbol, our book uses y equals its double struct square bracket of x. Okay, so these are kind of the last three functions that we're looking at for a little bit. So next what we're going to do is we're going to focus on piecewise defined functions. So we're going to focus on piecewise defined functions. So we're going to first evaluate how do we, if we're given a function that has a piecewise defined form and we're asked to find a couple different outputs, how do we do that? So let's define our function f of x equals, it's going to be three parts. We'll say it's 2x minus 1 if x is less than -1. It's x squared plus 2 if x is between -1 and +1. And it's x minus 5 if x is greater than 3. And we want to find what is f of -2, what's f of -1, what's f of 0, what's f of 2, what's f of 4. So we want to find all of these function outputs for that particular function. So what we do is we'll say, all right, for part A, we have f of -2. Part B, we got f of -1. Part C, we want to find f of 0. What we do is we have to go through and we have to look at each of these inequalities here, and we have to see which inequality is true for the input number here. So only one of these inequalities will be true at the same time. So when I have -2, -2 is less than -1. So this, when it input a -2, that's making x less than -1 is true. So that's how I know for this particular function, I use the top form of my line here. So I'm going to substitute x in to the top form of that line. So we get this equals 2 times -2 minus 1. That's -4 minus 1 which is negative 5. Okay, so for part B, we got, use a different color, we got f of negative 1. So we have f of negative 1. We say, all right, negative 1, it's not less than negative 1. It is equal to negative 1. So we're in this middle form because it's okay to equal negative 1. So that means negative 1 gets plugged into this form, the middle equation. So when we do that, we get, instead of x squared, we get negative 1 squared plus 2, which equals 1 squared. Oh, sorry, 1 squared. Negative 1 squared is 1 plus 2, which is 3. Then finally, we say we have f of 0, so we're looking at an input of 0. 0 is still in the second form. 0 is between negative 1 and 1, so we're going to plug 0 into here, this middle form. So when we do that, we get this is 0 squared plus 2, which is 0 plus 2, which is 2. All right, so for the last two, part D here, we want to know what is f of 2, and part E will say what is f of 4. So for f of 2, we say, all right, let's look for an input of 2. 2 is not less than negative 1. 2 is not between negative 1 and positive 1. And 2 is not greater than 3. So 2 is an input where none of the three forms of the line work for it. So this, whenever that happens, we say this is undefined. There was no form to plug it in because this 2 did not make any of these inequalities true. So for the last one, we say, all right, what about f of 4? What does f of 4 line up with? So what we do there is, so we got what's f of 4? We say, all right, 4 is greater than 3. So we plug it into this bottom form. So f of 4 makes the bottom part here true. So that tells me the form we plug into. So to plug it in, we say, all right, this will be 4 minus 5. So we're replacing x in the bottom form with 4. 4 minus 5 is negative 1. And that gets our answer, and that wraps up this problem. On the tests and on the final, they do like to give these types where there's a skipped value where it's undefined. But otherwise, that's kind of how these work. They're pretty straightforward. You just have to go through and look at your input number and check it and see which equation it makes it true. So these aren't too bad. Where these things get tricky is if you want to sketch. So this will be our next examples, or the last examples from this section, are what happens if you want to sketch a piecewise defined function. So we'll sketch one with two parts here. So we're going to be 2x minus 1 if x is less than negative 1, and will be x squared if x is greater than negative 1 or equal to negative 1. Okay, so here's how we sketch these types. First, we're going to say, all right, x equals negative 1 is when we stop being the top form and we start being the bottom form. So we're going to focus on negative 1. To figure out where this right here is the diagonal line, and this is a U-shape. To figure out where we stop being 2x minus 1, I'm going to take negative 1. I'm going to plug it in for x here. So when I do that, I get negative 2 minus 1 is negative 3. So for an input of negative 1, I have a y value of negative 3. And since there is no or equals here, I'm going to put an open dot down there. If there was an or equals underneath it, we'd use a closed dot. So let's maybe write that off as a little note here. If you have inequalities like this type or like this type, use open circles. If you have inequalities with the or equals under them, then you're going to use a closed dot. So my graph is 2x minus 1 for all x is less than negative 1. So if this is negative 1 for the x value, that means for x equals negative 2 and negative 3, etc., my graph is this line here. Now, normally to get a second point on the line, we use rise over run. So we would use the slope of this line here is 2 over 1. So we'd view that as rise over run. And we would say, okay, rise of 2, a run of 1. So that would mean if I go up 2 units, I go to the right 1 unit. And that gets me another point my line passes through. The problem here is this is on the wrong side of where we're keeping. We're not keeping for x is 0. That's a different form of the line. So if you're going to view this as rise over run, we either need to make them both negative. So if I go down 2 units, I go down 1, 2 units, I go to the left 1, and that gets me a point that I know my line is going to pass through. Or what you can do is you can take an input like -2 that's from the region you know. You can substitute the -2 in for x here. And we would get -2 times 2 is -4, minus 1 is -5. So -2 goes 1, 2, 3, 4, 5. It gets us the same exact point. And then we're able to connect through that point, starting with the open circle, and say, okay, this part right here is the 2x minus 1 segment of our line. Now for the x squared part, this one has the or equal, so we're going to use a closed dot. I put -1 in there. -1 squared is +1, so I get -1, +1 with the closed dot. If I think about what x squared's graph looks like, x squared's graph is a basic parabola. I have the point -1, +1 with a closed dot. And I'm going to be keeping the, starting at that closed dot, I'm going to be keeping to the right, so I complete this part of the parabola. The part that was to the left, I don't keep that. That we did a different form of the line to the left of that dot. So I'm going to basically just make this shape here. And let's see, we'll pass through that point we mentioned earlier. And then this right here is the graph of that piecewise defined function. So we're going to do a second one of these with just 2 parts. Then we'll do one of these with 3 parts. And then that should be good for this section. That should wrap this section up. We'll move on to 2.7. All right, so for this example, we're going to want to sketch a function f of x that equals x squared if x is less than, let's say less than or equal to -1. You know, let's use a different number. It's x if x is less than or equal to +1, and its absolute value of x if x is greater than +1. So this time we are dealing with +1 is kind of the point where stuff changes. We have x squared. X squared's graph looks like a parabola. So I'm just making a quick sketch of x squared's full graph over here. If we input 1, 1 squared is 1, so we get the point 1, 1 basically with a closed dot. So we have the point 1, 1 on this graph. And for all x's less than that, so for all x's to the left, I want to make my graph have the parabola x squared shape. So for all x's through here to the left, I'm going to have my graph. Oops. I'm going to have my graph make our parabola shape. Okay. Now our graph turns into the function absolute value. Absolute value is a V shape. It also has point 1, 1. So I input 1, absolute value of 1 is 1. I'm going to use an open circle there. And I'm supposed to keep all x's bigger than 1, so I keep all x's to the right. So I keep this diagonal line portion. Thing is, there's already a closed dot where the open dot's going to go. A open dot will be filled in by a closed dot. So we treat the point 1, 1 that was an open dot here. When we try to put it on the graph, there's already a closed dot, so we treat it as a closed dot. And we're just going to give the rest of this expression that part of absolute value for its graph. And so this is what this piecewise defined function looks like. It's x squared to the left of 1, and then at 1 it changes and it becomes absolute value. So we'll do a piecewise defined graph that has 3 parts. Do a sketch of that. So we'll sketch f of x equals, will be a function that is 3 if x is less than or equal to -2. We will be negative x plus 1 if x is between -2 and +2. And then we'll be x cubed if x is greater than or equal to +2. Okay, so the line 3 is a horizontal line. So it's just a horizontal line here. For x equals -2 and all x values less than that, we want to be the line 3 with the closed dot. So we have a closed dot for x equals -2. And this is the part of that horizontal line 3 we are keeping that I've drawn in red. So over here in my actual graph, we say, all right, at -2, we have a y value of 3. So we're going to put a closed dot there, and we're going to draw a horizontal line off to the left. So that's my first part. For the middle part, we have -x plus 1. This is a diagonal line. Its y-intercept is +1. Its slope is -1. So if I go down 1, I go to the right 1. If I go up 1, I go to the left 1. And this right here is kind of my line. Okay. So when I input -2 with an open circle, so I input -2, negative -2 becomes +2, plus 1 becomes 3. So when I'm at x equals -2, I have an open circle here at 3. Should note that open circle -2, 3, that's the same place where the closed circle here is. So the closed circle will fill in the open circle when we go to draw it. And we're going to do this graph until we get to +2. And so at +2, -2 plus 1 is -1. So at +2, we're down here at -1. And we want to keep the segment in between these. This will be the part of that diagonal line we keep. It's the in-between portion between those 2 points. So at +2, the y value is down here at -1. And our line, we said the y-intercept was 1, so our line basically is a diagonal line doing that. So then to finish up, we say, okay, what about x cubed? I'm going to be, I stopped here with the closed dot. I need to stop there with an open circle at 2, -1, because we had an open circle there. The reason that this one was closed because we had open and closed, open dot and closed dot at the same spot. And when that happens, the closed dot fills in the open dot. So let me erase that little bit there, but that's what's going on there. So the last one, we got x cubed's graph. I'll draw it kind of right here. X cubed's graph looks like this. At 2 cubed is 8, so at x equals 2, the y value is way up here at 8. And we're going to use a closed dot, and we want to keep for x is greater than 2, we want just this part of the curve that heads upwards like x cubed. So for 2, let's see, here's 4, 5, 6, 7, 8. At x equals 2, the rest of our graph for the cubic is way up here at 8, and we're just going to move on with that cubic shape. So we don't get any of the interesting part of the cubic graph where it's going through there. We just get the part where it's slowly curving away upwards. try to draw this and do a better job of it. So we get basically that. It's the curve part there, and this is our graph for this three-part function over here. So I think we'll stop on section 2.6 there. So stop there, and we'll move on to 2.7.